Alright, and so this is going to be the second video for the second part of 6.3. In the last video, we actually ended up proving the other direction, that if we have a vector field that is path independent and we're talking about an open and connected domain, that we actually have that the vector field is also conservative. So that was really nice. Now I'm kind of wondering about the derivative matrix component too. So remember, we had that summary. So is that one if and only if? Well, we need to do a little bit more discussing before we get there. Okay, so we will work up to a big theorem here. But we need one important mechanism. Okay, so first there's a definition that we need to be aware of, and it is this idea of circulation. And so we think of a path as being a closed path. Okay, so this isn't necessarily to say this is the same topological close, but it's just a closed path, such that if we look at the starting of the point, or starting of the path and ending of the path, they're the same, and that should actually have a vector over it. Apologies for that. Then when we talk about the vector line integral on that closed path, the vector line integral we talk about as what we call a circulation of f along the path. And notationally, you'll often see that it's an integral, and then there's this circle in the middle of the integral. This just means it's a circulation, that we have in a sense, a loop. And so we say, and C is the curve that is parameterized by X. Okay, so circulation, closed path, we need that idea. Okay, so now we have a continuous vector field, and again we have those assumptions of open and connected, just as we did in the last video, open connected domain of Rn, and then the following ideas are equivalent. So we have f is path independent, is the same as f having no circulation. Okay, and then just so we're all on the same page as far as what that means, if it has no circulation, that means that really, when we look at the circulation of the vector line integral, okay, this is equal to 0. And this is for all closed curves C. Okay? And so the proof is either really short or non-existent, and I'm going to tell you we're going to do this in group work. Okay? Or at least the ideas, and then maybe you might see it in your homework. We'll see. Just as a hint here, okay, this might be relevant for homework. Your hint is that for a curve C, that if we have the opposite of C in f dot ds, so we're doing the vector line integral. Okay, and all this means, all this notation here means minus C. It's the opposite direction, so you're going in the opposite direction. This is the same as saying negative of C of f dot ds, and we did this is a result of a proof that we did a while ago. Okay, or a theorem, I'm sorry, that we did a while ago. Okay. Alright, so we have that path independence and no circulation are same idea. So we have path independence, same as no circulation, same as conservative. Okay, what about this derivative matrix? Okay, well, my proposition, so I'm saying it's proposition because I'm not proving it to you, is that, okay, if we have a C1 vector field on a, now we have the descriptor simply connected open domain, okay? Then if that derivative matrix exists and it's symmetric, okay, so df symmetric, then f has no circulation. Okay, but we have to remember, okay, no circulation means, this means path independent, which means that we have conservative vector fields. Okay, so this is, with these suppositions, that is enough. So open simply connected domain, that's enough to say that these ideas are all equivalent. So our final summary here is that if f is C1 in an open, simply connected domain, if we have df symmetric, that's the same as f being conservative and conservative. And that's the same as saying f is path independent. Okay? And that's the same as f having or has no circulation. Okay? And there's a lot of assumptions floating around here, so when you are doing your work, be very, very, very careful about checking these hypotheses. Okay? And I do need to see that in your homework you are checking, like you explicitly write it out, like this is path independent, this is connected, this is open. You need to write that work down to tell me that you checked it. Otherwise, I'm just going to say you're pulling something out of your hat and it's coming out of nowhere. Okay? So make sure to check all those assumptions. I'll also mention that open was, let's undo that. Open you need in all of them. That's qualifier of simply connected. That only applies with that derivative matrix. So again, these other ones, F conservative implies path independence, that you don't need simply connected for. Similarly with no circulation. It's just for that derivative matrix, or that DF, you need that to be on a simply connected domain. Okay? Otherwise, that's going to conclude this video, and the remaining videos you might have noticed are all examples. So let's dive into those.